Welcome back to another video about convergence testing for infinite series. In this video we're going to talk about the ratio test. And the ratio test is a test that we like to use when we have certain situations arise. And one of those situations is when we have what's called the factorial function floating around in our series. And so let's talk a little bit about what a factorial is. So this little exclamation point is called a factorial. It doesn't mean that the 5 is super excited, although factorials are very exciting. What the factorial function is, or that exclamation point, it just means I'm going to take my value, my number, and I'm going to multiply it with every integer value all the way down until I get to 1. So for example, 5 factorial is simply 5 times 4 times 3 times 2 times 1, or 120. Now, your calculator has a factorial function on the TI-84s. If you hit the math button, I believe it's over in the probability option, so you'll kind of have to like go scroll over to the PRB, and then you'll see it's option number 4. So there is a factorial function in the math options of your calculator. Desmos will also evaluate factorials. So 10 factorial would just be 10 times 9 times 8. They get really big really fast, and I don't know that I have the time or desire to multiply this out. But one of the important skills that we need in the ratio test is to know how to simplify factorials. And so essentially, if I have these two factorials, remember that 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2 times 1. And then 5 factorial is simply 5, 4, 3, 2, 1. And if it's all multiplication, what I want you to see here is that essentially everything here is going to cancel away. And so you're left with everything above 5 factorial. So another way we could write this is simply 5 factorial. And if this is 5 factorial, we know that they're going to cancel away. And anything higher than 5 is what's left. Now, this gets a little trickier when our numbers turn into variables. And so if we have something like this, where we have n plus 1 factorial, if I were going to write this out, I want to write it out like this. I'd do n plus 1, and then you guys, if n plus 1 is the first value, remember the one that comes after it is 1 less. So 1 less than n plus 1 is n. 1 less than n is n minus 1, and so on and so forth. But what I want you to see is that just like up here, where we could do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, we could have written 10 factorial as 10 times 9 factorial. We could have written it as 10 times 9 times 8 factorial. And so what I want you to see here is that if I have an n factorial on the bottom, I'm not going to write that out, but I am going to remember that everything below n plus 1 can be expressed as n factorial. So what I can do is I can actually cancel away anything below my highest number in the factorials. So this simply turns into just n plus 1, because that's how factorials work. And so we're going to see that play out in our ratio test. So here's another little example. So n plus 3 factorial, I'm going to remember that this is n plus 3, and then the next one that comes after it is n plus 2. It's 1 less. So 1 less than 3 is 2. And the next one that comes after it is n plus 1. Now, everything after that is just going to be n, and then n minus 1. But I'm not going to write all that out, because I see that in the bottom of my fraction, I have an n plus 1 factorial. I'm just going to remember that everything below n plus 2 is just n plus 1 factorial. So I'm going to simplify that, and then I'm going to go and I'm going to cancel those two values. So what does this simplify to? It simply simplifies to n plus 3 times n plus 2. And that's how factorials work. And we're going to see that play out in our ratio test a lot. So let's talk about what the ratio test is. So what are the conditions for use of this ratio test? Well, the terms have to be positive. Surprise. The best time to use this. Okay. The best time to use this test is when our series looks almost geometric. So remember, if the series looks geometric, but it's like off by a +1, well, then, we can use like a limit comparison test or something like that. But when I say almost geometric, I mean like maybe it's got 2 to the n, and then there's a 3 to the n in the bottom, but there's like an n there, or something like that. So it's almost geometric. Or like when our series involves lots of factorials, that's going to be an indicator that we want to use this ratio test. So how does it work? Well, first thing we do is we state our condition, so the terms are positive. So in other words, it's not an alternating series. But then what we do is we determine the limit as n approaches infinity, and this is tricky, the an+1 term. So we're going to have to do some algebra, divided by an, and we figure out what that equals. It's going to come out to a value. So it could be infinity, it could be 0, who knows. But essentially, here's what happens. When you see how we interpret our results, I want you to think about the geometric series test and how we had r, and how when r was bigger than 1, our geometric series did not converge, it diverged. And when r was less than 1, our geometric series converged. But r in a geometric series can't be 1, because when you have 1 to a power, you just literally get 1 plus 1 plus 1. So in a geometric series, if r was ever 1, we'd say that the series diverged. There's a subtle difference here, and here's what the ratio test, here's how we interpret the ratio test. What we do is we look at the value of L, and basically here's what happens. If L equals 1, our test is inconclusive, and we have to try something else, okay? So if L is ever equal to 1, that's an inconclusive result. We just can't use the ratio test. And there's going to be times when you try the ratio test because you're going to be like, oh, I love this test. You're going to try it, you're going to get 1, and then you're going to be sad because you've done all that work for nothing. And then you have to go do limit comparison or some other test or direct comparison or something like that. So just be mindful, if you do the ratio test and you get 1, you got to start all over. So sorry. But if we do the ratio test and we get a number that's less than 1, well, then our series converges, just like a geometric series. And if we get an L greater than 1, then the series diverges. So just like a geometric series. The only subtle difference is that if we're equal to 1, that means that our test is inconclusive and we have to try something different. Okay? So think of your L value as like R in the geometric series. So let's take a look at how this plays out. So first things first, I've got this series. It kind of sort of reminds me, kind of sort of geometric. I've got a power of n. Okay, so here's what we do. We have to do the limit. So the terms are positive. So first of all, terms are positive. Actually, my first term will end up being 0, but the terms are positive, or non-negative, I guess is the right way to say that. And so now here's what I'm going to do. I'm going to find the an+1 term, and I'm going to compare it to the an term, and I'm going to do that limit as n approaches infinity. So here's what it looks like. When I find the n+1 term, I'm literally going to plug n+1 in for n. So it kind of looks like this. an+1 is going to be n+1 squared minus 1, and then 2 to the n+1. So take it in, convince yourself that it's true. So now I'm going to put that in place, and the n+1 term always goes in the numerator. Now on the bottom, I just put the original function. I'm going to use some parentheses so I don't get mixed up. Now every time I do this ratio test, the denominator is almost always going to get flipped. There's a few times when we don't need to worry about that. But 9 times out of 10, this bottom ends up being a fraction, and I'm going to have to flip it. So I'm going to go ahead and flip it, 2 to the n over n squared minus 1. All right, now it is time for some fancy algebra. So Oh, and I left out a limit. Oh my goodness. Almost had a linkage error. All right. So here's what's going to happen. In the numerator, that n plus 1 squared is going to get multiplied out. So I'm going to have n squared plus 2n plus 1 minus 1. Now in the denominator, watch what I do. Every time I have a power, so here I've got a 2 to the n plus 1. Whenever I have a power like that, I'm going to split it up and make it 2 to the n times 2 to the 1. That's what I'm going to do every time I have a power when I'm doing the ratio test. And you'll see why in just a moment. So now I'm going to multiply 2 to the n, and then I've got n squared minus 1. And I'm going to throw my limit in there so I don't get a linkage error. All right, now watch what happens. You're going to start noticing that I'm going to have 2 to the n and 2 to the n, and those are going to cancel away. So this plus 1 and this minus 1 cancels away. So now let's write what we have left. I've got the limit as n approaches infinity. I've got n squared plus 2n left in the top, and on the bottom I've got a 2, and then I've got n squared minus 1. Now I'm approaching infinity, so the name of the game here is end behavior models. So I'm going to do the limit as n approaches infinity, and I'm going to pick the dominant term in the top and the dominant term in the bottom, and lo and behold, this limit ends up being 1/2. Now, I'm ready to interpret my result. So this value, just like the geometric series test, this value is less than 1. Therefore, my series is going to converge. So all I have to do is say why I know that this series converges. I'm going to show my result. I have to show the 1/2, so the number that I get has to be correct. And then I have to say this is less than 1. Without that less than 1, you haven't really said that you know this test. So you have to say because it's less than 1. So now I'm ready to say therefore, I'm going to say the series n equals 1, 2 to the n converges. Ta-da! There we go. So by the ratio test, we know that this series will converge. Usually the ratio test involves series that have really ugly terms. So like when you start looking at ratio test problems, like this is not a very pretty looking series, and this is not a very elegant, it's very complex, lots of factorials. Oh, lots of powers, look at that one, factorials and powers. That's usually an indicator that the ratio test is what we want to use. So let's try this next one. Let's do our ratio test for this problem. Now, for this one, sometimes we look at it and we say, oh, this looks like an integral test because it's a tabular integration. But as soon as we have that factorial floating around in there, the ratio test is almost always what we're going to want to try. So what I'm going to do here is I'm going to say, okay, my terms are positive. Okay. And then what I'm going to do is find the limit as n approaches infinity. And now if I have a negative exponent, I'm going to just rewrite this as n factorial over e to the n. I'm going to get rid of that negative exponent. So here we go. I'm going to do the n plus 1 term. So I'm going to plug in n plus 1 factorial and then e to the n plus 1 divided by the original series, n factorial over e to the n. Now, just like I did in the last one, I'm going to flip that series. And anytime you have a situation where you have a fraction and you're going to have like a double-decker fraction like this, you are allowed to just jump straight to this step. And as a matter of fact, you'll see in the scoring guidelines for a lot of FRQs, they just skip making a ratio and they just jump straight ahead to flipping that an term because they know that that's what's going to happen. So if you want to jump to that conclusion as well, you're more than welcome to. Just recognize that it's not always going to be a double-decker fraction, so we do need to recognize that it's a ratio. So now I'm going to do a little simplifying. So here we go. The limit as n approaches infinity. So this n plus 1, I'm going to rewrite it as n plus 1 times n factorial. I'm going to split the bottom. And in working with these factorials, whenever I have an n plus 1 and then an n factorial, I'm going to remember how they're supposed to simplify and how they're supposed to reduce. And if I just write it out like that every time, ta-da, that cancels, ta-da, that cancels. So exponents, split them up. Factorials, write it out until you get a factorial that cancels. Then we're going to regroup whatever we have left. So we have n plus 1 over e. And oh, by golly, this limit approaches, let's double check that I didn't miss anything. This limit approaches infinity. Therefore, the given series is going to diverge. So we kind of are getting a sense for how this ratio test is working and what we need to do to support our answer. So let's see another one. All right, so here's our next example. And for this one, I see factorials. So again, ratio test, factorials, they love each other. So the terms are going to be positive. And so now I'm going to set up my ratio. So the limit, all right, so now it's a fraction. So I'm going to go ahead and take that step of jumping to the conclusion where I flip that an term. So I'm going to put n plus 1 in for all my n, so n plus 1 factorial. Now this one is a little special because I have to do n plus 1 in for n, and then plus 1. Times, and now I'm just going to go ahead and flip the original. Okay, now I'm going to write out my factorials so that I can simplify things a little bit better. So I'm going to have n plus 1 times n factorial. And then in the bottom here, let's see, this will be 2n plus 2 plus 1. This is going to be 2n plus 3. And then 1 less than 2n plus 3 is 2n plus 2. And then 1 less than that is 2n plus 1. And that's where I'm going to stop because I see that in my an term, that's what I have going on. So whatever I have right here and right here, that's how I know to stop when I'm expanding that factorial. So now I'm going to go ahead and cancel those terms. So n factorial and n factorial, 2n plus 1 factorial, 2n plus 1 factorial, that's going to cancel. So now I'm going to write what's left, the limit as n goes to infinity, n plus 1, all over 2n plus 3, 2n plus 2. And now I'm going to use an n behavior model. N goes to infinity. I'm going to have n in the top. And then the n behavior model is going to be 4n squared. So this is going to go to 0. And 0 is less than 1. So by the ratio test, the given series converges. Ta-da! That's how that works. So the trick with the ratio test is knowing how to do factorials, knowing how to work with algebra. There's a lot of algebra involved in this particular test. So let's take a look at one last ratio problem. We'll take a look at this one right here. Okay, so our terms are positive. Check. So now let's set up our limit. So the limit as n goes to infinity. So we're going to put in n plus 1. So it's going to be n plus 1 plus 3. And then it's going to be n plus 1 factorial. And then it's going to be 3 to the n plus 1. And I'm going to go ahead and jump to that where I flip the bottom. Save a little space and time. Now I'm going to start expanding all my factorials. This is n plus 4 factorial. So I'm going to do the limit as n approaches infinity. I'm going to have n plus 4 and then n plus 3 factorial. And that's where I'm going to stop because that's what I have in the bottom of the term that's going to kind of cancel some things away. And then over here, I'm going to have n plus 1 times n factorial. And then I'm going to split up 3 to the n times 3 to the 1. And then that's going to multiply with that n factorial, 3 to the n plus 3 factorial. Now I'm just going to cancel. So cancel, 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 n factorial. Now let's write what's left. Got n plus 4, and on the bottom I've got 3, and then n plus 1. I'm going to use an n behavior model. I got n over 3n. Oh, that limit is 1/3, which is less than 1. The given series converges. Ta-da! So, again, that ratio test is all about being able to do algebra, being able to split your exponents, being able to write out your factorials, and then being able to cancel things. So watch out for your algebra, take it slow, and this is a really important test. So knowing how to do this is going to be very helpful as we move into the second part of Chapter 9. It's going to play a very critical role in finding some information that we need to find in Chapter 9, Part 2. So make sure that you're practicing this, and yeah, keep at it. You got it.